Welcome back. This is the second part, Part B, of a video lecture on Section 2.3 from the textbook, Spanning Sets and Linear Independence. In a previous video, we talked about spanning sets of vectors, and so today we're going to finish up this section by talking about linear independence. The concept of linear independence is at the core of any course in linear algebra or any course on matrix and vector theory, so it is a central topic. Nonetheless, it is a somewhat mysterious topic, so what I want to do is approach this topic somewhat obliquely. So let's consider this problem first. Let u1, u2, and u3 be vectors in n-dimensional space. Now we always have that the span of the three vectors u1, u2, and u3 contains the span of the two vectors u1 and u2. So why is that true? Well, let's think about why this must be true. If I ever want to show set containment, if I want to show that this set here on the right is contained by the set on the left, all I have to show is that a typical element in this set is already contained in this set. So this is one way, this is probably the chief way that we're going to prove set containment. All right, what does it mean to be in the span of u1 and u2? It means that there are some scalars a and b so that the vector in question is of the form a times u1 plus b times u2. So anything in the span of u1 and u2 can be written as a times u1 plus b times u2 for some scalars a and b. Now what we have to do is we have to show that such a vector can be written now as a linear combination of u1, u2, and u3. So here's what I'm going to do. I'm going to take my vector of the form a u1 plus b u2, and I'll write it as a u1 plus b u2 plus 0 times u3. That shows in a very trivial way that it can always be expressed as a linear combination of u1, u2, and u3. All right, so clearly that shows that anything that's spannable by u1 and u2 is also spannable by u1, u2, and u3. All right, the question we're after, though, is this. What are the conditions on u3 to guarantee that the span of u1, u2, and u3 is strictly a larger set? What would I have to know about u3 to know that this collection is actually bigger? It contains elements that aren't already in the span of u1 and u2. So what do I have to know about u3 to know that I'm actually opening up some new ground, that I'm now containing elements that I couldn't contain before with just u1 and u2 alone? So that's the question. What do we have to know about u3 in order to guarantee that that span, the span on the left, is strictly bigger than the span on the right? Our next problem answers this question. Let u1, u2, and u3 be vectors in n-dimensional space. We want to show that u3 is in the span of u1 and u2 if and only if the span of u1, u2, and u3 equals the span of u1 and u2. Now let's see how this helps us answer our question. We know that if the span of u1, u2, and u3 is equal to the span of u1 and u2, in other words, if this is not a strictly larger set, then the condition must be that u3 is already in the span of u1 and u2. On the other hand, if this is a strictly larger set, if these are not equal to each other, then this set is strictly larger. There are things in this left-hand side that are not in the right-hand side. So if this is a strictly larger set, if these are not equal to each other, then it must be the case that u3 is not in the span of u1 and u2. Now, we can see this in a picture. We're going to go to the document camera and work this out, but we can already see it in a picture here. So in the picture on the left here, I've got my two vectors u1 and u2, and we can think of them as kind of sweeping out this green carpet, a two-dimensional green carpet that they can sweep out. Everything in the span of u1 and u2 is reachable on this kind of flat plane. And in this picture, I've got u3 in the span of u1 and u2. It's explainable by u1 and u2. It's reachable by u1 and u2. And in this case, adding u3 to the mix and looking at the span of u1, u2, and u3 never gets us outside of that green carpet. We're still stuck in the plane. On the other hand, if u3 is not expressible in terms of u1 and u2, in other words, if it's not in the span of u1 and u2, then we believe that adding it to the mix and now looking at the span of u1, u2, and u3 brings us into another dimension. We are now reaching vectors that we couldn't reach before. And so that's the content of this problem. It's helping us understand the difference between these two pictures. All right, so let's head over to the document camera and work out the solution to this problem. Welcome to the document camera. Let's look at the proof of this problem, right? We've got this statement that says u3 is in the span of u1 and u2 if and only if the span of u1, u2, and u3 is equal to the span of u1 and u2. Now remember, this is an if and only if statement. And so there are two directions of implication. I have to show that if this is true, then this is true. And if this is true, then this is true. So let's prove this forward direction first. I'll just symbolize it by that. We're going to prove that if this is true, then this is true. So we're going to assume that this is true. So we'll assume that u3 is an element of the span of u1 and u2. And right away, let's just make sure we understand what that means. To say that u3 is in the span of u1 and u2 means that it's a linear combination of these two. Therefore, u3 is equal to, let's say, a1 times u1 plus a2 times u2. So I know that u3 can be expressed in terms of u1 and u2. Now, that's a fact in evidence. I have to now show that if that's true, then this must be true. Now, generally when you want to show that two sets are equal, you have to show two things, right? There would be two things typically to show. The set on the left contains the set on the right. And the set on the right contains the set on the left. All right, so there'd be two things typically to show when you want to show that two sets are equal to each other. Now, one of these we know is automatic, this one. We know that since this collection of vectors u1, u2, and u3 already contains this collection, that the span of u1, u2, and u3 must be containing the span of u1 and u2. So this one we already know. We now have to show this one. And how do we show that one set is contained by another? We have to show that if I take something out of this set, that it can be represented by something in this set. All right, so I have to take something out of this set. So let x be a vector in the span of u1, u2, and u3. And what does that mean? That means x can be written as a linear combination of u1, u2, and u3. Now let's use the symbols b for those scalars. Okay, so to say that x is in this set means it's of this form. Now what I have to show is that x, in fact, can be written only in terms of u1 and u2. That would put it into this set. And what's my secret? Well, I know how to write u3 in terms of u1 and u2. So all I'm going to do is go in here, and in place of u3, I'm going to use this instead. Okay, that's the crucial move right there. Since this is true, I am free to use it in place of U3 right there. And so that's how I introduce this. I can replace U3 by AU1 plus A2U2. A1U1, A2U2. Okay, good. Now, the only thing we have left to do is to distribute the scalar and then collect our terms together. All right, I'll do that in 2 steps. You can do it in 1 step, but I'll do it in 2. So we can think of this as a single scalar that's multiplying U1, and that's going to be the B1 plus the B3A1. And multiplying U2 will be a single scalar, B2 and B3A2. And now we're done because that means X is in the span of U1 and U2. Okay, that proves the forward direction. Now that is the hard direction as it turns out. So if we're thinking about these 2 implications, they're not of equal difficulty. Proving this forward direction is the more intense direction. Proving the opposite direction is not as hard. Let's take a look. Now in this case, I know that these 2 sets are equal, and I have to show that I can write U3 as a linear combination of U1 and U2. All right, now these 2 sets are equal. Now one of the vectors that I know is in this set is U3. Okay? One of the vectors that I know is in the span of U1, U2, and U3 is in fact the vector U3. So we're going to say something like this. If the span of U1, U2, and U3 in fact is equal to the span of U1 and U2, then U3 must be in the span of U1 and U2. Okay? Because that's one of the vectors that's in this left-hand side. So U3 has to be an element of that. So U3 is in the span of U1 and U2, and that's exactly what I wanted to show. So that direction is much simpler, much more straightforward. Okay, so the real difficulty, or the real kind of important part of this is this direction, right? It says if U3 is spannable by U1 and U2, then adding it to this collection doesn't increase the span. It doesn't buy us anything new. We don't increase the span at all. Okay, and you can kind of see within the argument why. Anything that involves U3 is replaceable by things that involve U1 and U2. So U3 is not adding anything new to the mix, so to speak. Okay, I hope you enjoyed the solution to that problem. I hope you learned something from that. Let's head back to the class notes. This is one of our most consequential definitions of the semester. So we're going to study this definition and work out some of its consequences. All right. A set of vectors v1 through vk is declared linearly dependent if there are scalars c1 through ck, and this is important, at least one of which is not 0, such that the linear combination c1v1 plus c2v2 on out to ck times vk equals the 0 vector. In other words, there's a way to combine these vectors. There's a linear combination of these vectors that brings us to the 0 vector in such a way that at least one of the scalars is not 0. So that's the definition of linearly dependent. A set of vectors that is not linearly dependent is called linearly independent. Now, the reason why we have to pay special attention to this little clause here, at least one of which is not 0, is for the following reason. There's always a way to form a linear combination of these vectors that produces the 0 vector, and that's by taking the trivial choice. C1 is equal to 0, C2 is equal to 0, and ck is equal to 0. So in other words, we can always choose all of the scalars to equal 0, and the corresponding linear combination will equal the 0 vector. But that's considered a trivial choice of coefficients. That's obvious. It's trivial. What this is saying is that when the vectors are linearly dependent, there's a non-trivial choice of scalars that produces this result. So there's a non-trivial choice of scalars so that this linear combination is resulting in the 0 vector. Okay, so the idea of linearly dependent is an important concept. We're going to work on some of its consequences, and the first and most important consequence of this is embodied in our next theorem. Here's theorem 2.5. The vectors v1 through vm in n-dimensional space are linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the others. We're going to go to the document camera and work out the proof of theorem 2.5, but before we do that, let's try to connect the result of theorem 2.5 with a concept or a discussion that we had earlier when we started our discussion of linear independence. So the question is here: are all of the vectors in the span of v1 through vm necessary? In other words, can we eliminate some of them and still span the same set? All right, in other words, are there some vectors in here that are in some sense superfluous, playing no essential role in forming the span of the collection? Now, if you remember from a discussion that we had earlier, the vector v2 could be eliminated, for instance. It could be eliminated without destroying the span if and only if it's a combination of the others. So if I could write v2 in terms of the other vectors, then I could safely remove it from the span without reducing the span at all. So v2 in some sense is inessential or unnecessary. So in general, if there's any vector in this collection that can be expressed as a linear combination of the others, then it can be safely removed from the span without reducing the span at all, without destroying the span at all. All right, but that's precisely the question that theorem 2.5, or that's precisely the issue that theorem 2.5 is addressing. It's telling us that if one of the vectors can be expressed as a linear combination of the others, then that must mean that the collection is linearly dependent. But on the other hand, if none of the vectors can be expressed as a linear combination of the others, then the collection must not be linearly dependent. It must in fact be linearly independent. So, if I look at my collection and it's linearly independent, then every one of these vectors is necessary. I can't remove any of them without destroying the spanning property. On the other hand, if I look at this collection and I find that it's linearly dependent, then I know that there are some unnecessary vectors in there. There are some vectors in there that are not doing anything essential. They're unnecessary. All right, so the question of whether we can eliminate vectors is tied up with the question of whether the collection is linearly dependent or not. Okay, so I hope that helps you understand what the role of linear independence and linear dependence plays. Let's head over to the document camera and look at the proof of theorem 2.5. Welcome back to the document camera. Let's remember what theorem 2.5 is saying. It says the collection v1 through vm is linearly dependent if and only if one of the vectors is a linear combination of the others. And this is the usual if and only if statement. So there are two directions of implication. Let's prove this direction first. Let's do the forward direction first. So we'll begin by saying that asserting this claim that v1, we'll say the collection v1 through vm is linearly dependent. Now, what does that mean? According to the definition, that means that there is a non-trivial set of coefficients that produces a linear combination of these vectors that produces the zero vector. we'll call them scalars, C1 up through Cm, such that that linear combination of these vectors according to or with these scalars is equal to the zero vector. Okay, now I want to emphasize this word non-trivial. Obviously, these scalars could all be chosen to be zero, but that's not what we're doing here. We're saying that at least one of these is different from zero. So one of these coefficients is different from zero. All right, so let's just say for the sake of argument that C1 is the one that's different from zero. Now, it might be C2, it might be C3, it might be the last one, but that's actually not germane to the argument. The argument is that we know that one of them is not equal to zero. Let's just say, to keep the argument moving along and not make things overly difficult to articulate, let's just say that C1 is not equal to zero. You'll see that you could adapt the argument to any one of the coefficients being different from zero. So, without loss of generality, let's assume C1 is a coefficient that's different from zero. All right. And what we're going to do is we're going to use the fact that these are summing to the zero vector. We're going to move all of these other vectors except for C1, V1. We'll move them all to the right-hand side. Okay? And now here's the crucial step, right? We know that C1 is different from zero. So I'm going to multiply both sides. I'm going to scale both sides by 1 over C1. That's a well-defined number because C1 is not equal to zero. So scale both sides by 1 over C1. Now on this side, I can use my double scaling law. This is the same as 1 over C1 times C1, or 1 times V1. So this is just V1 on the left. On the right, I can distribute and use my double scaling law and write this as V1 equals minus C2 over C1 times V2 plus minus C3 over C1 V3 on out to minus Cm over C1 Vm. All right, so that's the crucial step there. Now, what are we seeing here? We're seeing that V1 is now being expressed as a linear combination of V2 through Vm, right? So V1, in fact, is the vector, right? It says one of the vectors is a linear combination of the others, and here we're saying, in fact, it's V1. Why is it V1? Because that's the one that had the non-zero coefficient. You see how you could adapt this argument to the case where C2 was the one that was non-zero. I would keep C2, V2 alone on this side and flop all the other ones to the right-hand side and repeat the same argument. So this is really without loss of generality. Whichever one of these coefficients is different from zero, you can keep it on the left and move everything else to the right and adapt this argument accordingly. No matter how you do it, though, you're going to be able to show that at least one of the vectors is a linear combination of the others. Okay, so that proves this forward direction. By starting with the assumption of linear dependence, we can show that one of the vectors must be a linear combination of the others. Now, let's prove the other part, right? If one of the vectors is a linear combination of the others, let's show that that forces the collection to be linearly dependent. And this is the easier part. Okay. Now, again, it could be any one of the vectors. I'm going to pick on V1. So let's, without loss of generality, let's assume that V1 is a linear combination of the others. Okay, and what does that mean? That means that there exist some scalars that I can write V1 as some scalings of those vectors added together, right? Right, there would have to be scalars C2 up through Cm such that V1 is expressible as this linear combination of V2 through Vm. Now the last step is just to move V1 to the other side as minus V1, or better as minus 1 times V1. Now I claim we're done, because what do we have here? We have a linear combination of the vectors v1 through vm. At least one of the scalars is non-zero. And according to our definition, that means the collection v1 through vm is linearly dependent. Which is what we wanted to show. So we showed that by starting on this side, we can achieve this side. The truth of this implies the truth of this. And so that completes our proof. We've got both implications shown. And that is the conclusion of this all-important Theorem 2.5. So let's head back to the class notes and continue. So let's work with this concept of linear independence and linear dependence. Here's a collection of 3 vectors in 2-dimensional space, and the question is, are the vectors linearly independent? So let's head over to the document camera and look at the solution to this problem. All right, welcome to the document camera. The problem that sits before us is to decide whether this collection of vectors, 1, 1, 2, 4, and negative 5, 9, is linearly independent. Yes or no? Okay, now we know what that hinges on. We have to see if there's a non-trivial choice of A, B, and C, some choice other than A equals 0, B equals 0, and C equals 0, that allows me to combine these vectors to get the 0 vector. Can I combine them in a way that takes me back to the origin, so to speak? All right. Now we know how to handle such questions. This is what we've been doing already in this section. If I want to know, is this vector a combination of these vectors, I can feed these vectors into an augmented matrix and look at the solution set. So let's take a look at what we get. We're going to take 1, 1, 2, 4, negative 5, negative 9, 0, 0. We're going to feed them into we're going to create an augmented system. And now we're going to look at the solution set for this augmented system. Now, I'm not going to bore you with the details because you're quite good at doing this by now. There's a sequence of elementary row operations that I can use to take this down to reduced row echelon form. And it's going to look like this by the time you're done. And you should check me on this. Okay, so there's the reduced row echelon form. And let's remember our columns correspond to the variables A, B, and C. Those are our scalars. And let's notice right away something interesting, right? This variable is a leading or a bound variable. This one is leading or bound, however you want to think of it. This one's free. And in a sense, the game is over, right? We know, in fact, that this collection must be linearly dependent. We know that right here. We could put our pencil down or our pen down and walk away. We could safely declare this collection is linearly dependent. Because the presence of this free variable says that at least I can set this one equal to anything I want, anything different from 0, and I'll have a non-trivial solution to this linear combination problem. All right, there will be a choice that's other than the trivial choice. So just the presence of the free variable allows us to walk away and declare that collection linearly dependent. But let's see what's really going on. This will give us a better understanding of what's going on. Let's explore the solution set a little bit. So we know that C is free, so we can kind of set C equal to some free parameter, let's say S. This equation down here is telling me that B is equal to twice C. So B minus 2C is equal to 0. So B is equal to twice C or twice S. The first equation is telling me that A minus C is equal to 0. So A is equal to C or A is equal to S. So our solutions are all going to be of the form C is equal to S, B is equal to twice S, and A is equal to S. So obviously if we choose S equal to 0, that's going to give us the trivial solution where all of the coefficients are 0. And obviously that is a solution to this homogeneous equation. But it's not an interesting one. It's not the one that's going to give us the proof of linear dependence. Let's make a choice that gives us something interesting. Let's set S equal to 1. When we do that, everything snaps into place. A is equal to 1, B is equal to 2, and C is equal to 1. And that gives us a combination that looks like this. I would have 1 times the vector 1, 1. 2 is going to scale the vector 2, 4. And 1 will scale the vector negative 5, 9. Now, if we've done our work correctly, this should add up to the 0 vector. That's how we chose these coefficients, right? That's how we chose the A, the B, and the C. Let's just check. 1 plus 4, that's 5, minus, this is minus 5, minus 9. 1 plus 4 minus 5 is in fact equal to 0. So that's giving me 0 on the first component. 1 plus 4, that's 1 plus 2 times 4, that's 8. So 1 plus 8, which is 9, minus 9 is equal to 0. So this does it, right? This shows us, in fact, the mere existence of the free variable allows us to get the conclusion that it's linearly dependent. But if we work out the solution set and pick out one in particular, any one other than the trivial solution, it actually allows us to find the coefficients A, B, and C that make this work. Okay, so it's kind of like a little bit of extra work, and we can kind of show what that particular, or we can show what a particular combination would be to get us this result. Now, clearly there are infinitely many choices for A, B, and C that we can make, but we're interested in the one that's other than the trivial solution. So there you go. All right, let's head back to the class notes. Here's another problem of the same type. Here are some vectors in three-dimensional space. So is this collection of vectors linearly independent? Let's head over to the document camera and look at the solution to this problem. All right, welcome back to the document camera. The problem that sits before us is to decide whether this collection of vectors is linearly independent or linearly dependent. And this is just like the problem we worked. We're just in R3 instead of R2. We've got these three vectors in R3. Now, right away, we can simply lift all of these vectors out and create the associated augmented system. So we're going to have 1, 4, 1, 2, 9, 1, 0, negative 1, 4. That'll form the coefficient matrix. We'll have our constant of columns on this side, and in this case, it's a homogeneous system, so they're all 0. All right, now we know we're looking for a solution, A, B, and C, that will solve this homogeneous system, and we know that we can work out the solution set for this system by going all the way down to the reduced row echelon form. Now, I took the pains of doing that already. You know how to do that by now. And here's what we get. We get a 1, 0, 0, 0, 1, 0, 0, 0, 1, and then, not surprisingly, a column of zeros on that right-hand side. Okay? Now, remember our columns are A, B, and C, and there are no free variables in this case. Each and every column contains a leading entry, a leading 1. And in this case, we can actually see right away what the solution is. The only solution to this system is A equals 0, B equals 0, and C equals 0. And that means that the only solution is the trivial solution, right? The only way to get these three vectors to combine to the 0 vector is the trivial solution. So since the trivial solution is the only solution to this equation, in fact, these vectors are linearly independent. All right. So if you combine these last two problems, if you look at them together as a whole, what do we discover? Well, we take our vectors, feed them in, that they form the coefficient matrix. We take the column vector of zeros and put it in on the right-hand side of our augmented system. So this is a homogeneous system. We do elementary row operations. We get it down to its reduced row echelon form. And what do we find? If there are no free variables, then the only solution is the trivial solution, and the vectors are linearly independent. But if there are free variables, then in fact the system has non-trivial solutions, and in fact the variables are dependent, linearly dependent. Okay, let's head back to the class notes and study that concept in a little more detail. Now, Theorem 2.6 summarizes what we've already discovered in the solutions to our last two problems. So this should look pretty familiar by the time we're done with our statement of Theorem 2.6. So let V1 through Vm be column vectors in Rn. So we're picturing m vectors represented as columns. And let A be the n by m matrix obtained by taking the vectors V1 through Vm and making them the columns of our matrix. So here's the crucial statement of the theorem. Then V1 through Vm are linearly dependent if and only if the homogeneous linear system with augmented matrix A forms the matrix of coefficients and our column of constants is just the 0 vector. If that augmented system has a non-trivial solution, then these vectors are linearly dependent. And if this augmented system has only the trivial solution, then these vectors are linearly independent. Now, this is exactly what we saw in our last two problems, right? That everything hinges on the solution set to this homogeneous system. Now, remember, a homogeneous system always has the trivial solution. So the real question is, does it have more than the trivial solution? If it has only the trivial solution, then it must be that these vectors are linearly independent. But if it has something other than the trivial solution, then it means that these vectors are in fact linearly dependent. So this becomes, Theorem 2.6 becomes our test, or a test, let's say, a test for linear dependence and linear independence. It says, form a system, a homogeneous system, look at its solution set, and depending upon the solution set, whether it has only the trivial solution or something other than the trivial solution, that will tell us about the linear independence or linear dependence of that collection of vectors. Okay, so this is one way that we'll use Theorem 2.6 as a way of testing linear independence and linear dependence. Theorem 2.7 provides us with another way of testing linear independence and linear dependence. This is a very different technique. So let's take a look at Theorem 2.7. This will be, in some sense, an alternative method than that presented in Theorem 2.6. So let V1 through Vm be row vectors in Rn, and let A be the m by n matrix we obtain by putting the vectors V1 through Vm this time as rows rather than columns. Okay, so we've got to adjust our thinking here. We're going to place the vectors v1 through vm as the rows of the matrix A rather than columns. Okay, here's the crucial bit. Then v1 through vm are linearly dependent if and only if the rank of A is strictly less than m. All right, let's unpack this a little bit. Let's remind ourselves of what this condition would essentially mean. All right, so I'm going to take my matrix A, and what am I going to do? I'm going to take it and put it into its reduced row echelon form. Okay, now if there's not a row of zeros at the bottom, that means that every single row contains a leading entry. In the case of the reduced row echelon form, a leading 1. Okay, if that's the case, then A has full rank. Its rank is equal to m. So if the rank is equal to m, then the vectors must be linearly independent. But if there is at least one row of zeros at the bottom, then the rank will be strictly less than m. There will be fewer than m leading entries, fewer than m leading ones, and the rank of A will be strictly less than m, and these vectors must be linearly dependent. So this gives us a second way of testing linear independence and linear dependence. We form the matrix whose rows are the vectors in question. We put that matrix into reduced row echelon form, and we look to see if there's a row of zeros at the bottom. If there is, they're linearly dependent. If there isn't, they're linearly independent. Let's head over to the document camera to look at the proof of Theorem 2.7. Welcome to the document camera. I am going to show you a version of the proof of Theorem 2.7. I'm not going to show you the full proof because it's the kind of proof that produces more heat than light. I think I'll show you part of the proof. I'll give you an idea of how the full proof could work if you were willing to work out all of the details. So here's what I'm going to do. I'm going to show you that if the vectors v1, v2, and v3 are linearly dependent, then the matrix we get by feeding those in as the rows of a matrix must not have full rank. And what I mean by not full rank is its rank would be less than 3 in this case, right? So a matrix has full rank if it has if the rank is equal to the number of rows. And so I'm saying that this is not full rank. Now, I'm also going to cheat. I'm not going to show you the reverse implication. So the reverse implication is if this matrix does not have full rank, then the vectors must be linearly dependent. All right, so I'll only show you this direction. I won't show you this direction. And I'm not showing it to you for an arbitrary set of vectors, v1 through vm. I'm only showing it to you for 3. And since I'm cheating, I might as well cheat in one more way. So when we're going in this direction, the claim is that v1, v2, and v3 are linearly dependent. That means that there is some set of scalars, c1, c2, and c3, so that c1, v1 plus c2, v2 plus c3, v3 is equal to the 0 vector. That's what the meaning, and this would be non-trivial. There's a non-trivial choice of c1, c2, and c3 so that I could combine them to give me the 0 vector. That's the meaning of linear dependent. Now, I'm going to cheat in another way. I'm going to say, let's just assume that I know that c1, c2, and c3 take on some specific values, all right? So I'm going to assume that, for example, it's 2 times v1 plus, let's say, minus 1 times v2 plus 1 times v3. That's a particular choice of scalars that produces the 0 vector. So this is my non-trivial solution. Now I'm going to organize this. I'm going to write this as, you'll see why. I'm going to write this as v3 plus 2v1 minus v2 is equal to 0. So let's say we know that. Okay, now what I'm going to do, I'm going to start with my matrix with rows v1, v2, and v3. And I'm going to perform a couple of elementary row operations. And these elementary row operations are absolutely inspired, right? They're coming right out of this claim here that this combination is producing the 0 vector. My goal is to get a 0 row down here at the bottom, and so I'm inspired by what I'm seeing here. So my first elementary row operation is to take row 1, scale it by a factor of 2, and add it on to row 3. Now that's not going to have any change in row 1. It's not going to have any effect in row 2, so those will be unchanged. But what it's going to do is it's going to combine row 1 with row 3 to give me V3 plus 2V1. And you can kind of already see where I'm headed. I've already got that much sitting there in the bottom of this new row 3. And now what I'm going to do is I'm going to do another row operation, and you can try to guess what I'm going to do based on what you're seeing here. I'm going to take row 2 times minus 1 and add it on to the current row 3. Now this will have no effect on V1 or row 1. It'll have no effect on row 2. I am making another change in row 3. This time I'm taking minus 1 times row 2, which is V2, and I'm adding it down onto the third row. So I'm going to get V3 plus 2V1, and I'll get this additional minus 1 times V2. Now you can see this though, right? According to the fact in evidence, according to the linear dependence of these vectors and the fact that these particular coefficients give me a solution to this homogeneous equation, I now know that I've got a row of zeros sitting at the bottom of my matrix. And that means that the system does not have full rank, right? The rank is going to be 1 or 2 at most. So the rank is certainly less than 3. And that's what we wanted to show, right? When the vectors are linearly dependent, this matrix that we get by putting the vectors in as the rows, is not going to have full rank, okay? It also says the other direction, which I'm not going to show you, that when this is not full rank, then the vectors are linearly dependent. Now that, in fact, is the direction that we want to use, right? We want to test for linear dependence and linear independence by forming this matrix and checking its rank. So in fact, I'm not showing you the direction that we would most often use, but let me just say, suffice it to say that this argument is more or less reversible. And so you can go from the lack of full rank back to the linear dependence by kind of reversing this argument. So there are several ways in which I'm cheating, but I am showing you more or less the moral form of this argument. So if you want to see the full form, you can consult a more advanced book to see how this can be worked out in gory detail. But this is sufficient for now. And what I want to do is head back to the class notes, and I'll show you a problem where we put this to use. Let's put theorem 2.7 to use and see how it works. Are the vectors listed here linearly independent? So let's head over to the document camera and let's work this one out now using the result of theorem 2.7. So join me at the document camera for this solution. All right, so the question is this collection of vectors linearly independent? And now we're going to use our most recent result that says take these vectors, feed them in as the rows of a matrix, and check the rank of that matrix. See whether it has full rank or not. So what we're going to do, this is different from what we did before. We're now going to feed these in as rows and form this matrix. The rows are going to be 1, 0, 2, 1, 2, 3, 0, negative 1, 10, 9, 8, and 1. Okay, now you're going to go through a sequence of row operations. You're going to put this into reduced row echelon form, say. So you're going to go through a sequence of steps. And I did this off camera. You can check me on this. I would ask you to try this yourself. And what we find when we do all the steps to get it down to reduced row echelon form is we're going to get a first row of 1, 0, 2, 1. Our second row will be 0, 1, -4/3, and -1. And then the final row will be 0, 0, 0, 0. Okay? So the rank here is 2, which is strictly less than the number of rows, which is 3. And that means that the collection, in fact, is dependent. Okay? Now, what's lost here by doing it by this method is we know that the collection is dependent. What's lost now is what would be a solution to the equation, right? Would be a non-trivial solution. So if we call these vectors, let's call them u, v, and w. So somehow we know that there's a solution to this equation where these scalars are non-trivial, right? That's what it would mean to say that the collection is dependent. There's some non-trivial choice of A, B, and C. Now, what's lost in this is what are those scalars A, B, and C? So if we do this by treating these as columns and augmenting it with a column of zeros, when we work that out and row reduce that, we actually can dig out a choice of A, B, and C, a non-trivial choice of A, B, and C. Now, we don't have that. Now, that's actually not true. If we kept track of all of the steps that took us to this reduced row echelon form, we could work out the choice of A, B, and C from the row steps that we've taken. It's a bit more complicated. So if you really needed to find these coefficients A, B, and C, you'd be better served to feed these as columns into an augmented system, a homogeneous system. And that way, when you're done doing your row steps, you would have the A, the B, and the C, a non-trivial A, B, and a C that would solve this homogeneous equation. So this does serve the purpose, though, of telling us that these vectors are linearly dependent. Okay, so I hope that was illuminating for you. Let's head back to the class notes. Let's close this section with a statement and proof of Theorem 2.8. Let's close this section with the statement and proof of Theorem 2.8. Any set of m vectors in Rn is linearly dependent if m is greater than n. Now, in order to wrap our heads around this, in order to kind of understand what this is saying, let's look at some cases. For instance, this theorem is saying any set of 3 vectors in R2 is linearly dependent. Any set of 5 vectors in R3 is linearly dependent. Any set of 10 vectors in R7 is linearly dependent. So what the theorem is saying is something like this. Once I know the dimension of the underlying Euclidean space, so for an example, if I know I'm working in R10 or R8, the value of n sets a ceiling on how many linearly independent vectors you could possibly have in that space. So once I know, for example, that I'm operating in R5, I can have up to 5 independent vectors in my space. Once I exceed that ceiling of 5, I know that the collection must now be linearly dependent. So I can only stuff so many independent vectors into R8, for example. I can stuff 8 of them. But once I take a collection of 9 vectors in R8, I absolutely know that that collection is now linearly dependent. That's what Theorem 2.8 is saying. So let's head over to the document camera and look at the proof of Theorem 2.8. Welcome back to the document camera. Let's look at the proof of Theorem 2.8. So here's the setup. We've been given m vectors in Rn, but m is greater than n. So I think of this as kind of overstuffed. I've got maybe 3 vectors that I'm trying to stuff into R2. And what I want to show is that this necessitates, this collection, these vectors must be linearly dependent. That's what the theorem is telling us, is that we've kind of run out of room and we've forced dependency in this collection of vectors, v1 through vm. Now, the previous theorem gives us the key, right? It says take these vectors. If you want to test whether these vectors are independent or not, take those vectors and make them the rows of a matrix. So let's do that. Now I'm going to try to draw this in a way that suggests what's going on. If I'm taking these vectors and making them the rows, that means that this is going to have m rows, one for each vector, obviously. I'm trying to draw the picture the way it would actually look if you were ever working with some particular values for m and n. What you'd find is that the matrix would be taller than it is wide, right? That's what this condition is telling me. It says I have more rows than I have columns. So the number of columns corresponds to how many components this vector v1 has, and that's n. And the number of rows is given by the number of vectors I have in my collection. And we're told that that's more than the dimension of the Euclidean space. So our matrix is typically going to be taller than it is wide, right? That's what that condition is telling us. Now, what do we know? We're going to try to work out the rank of this matrix, right? The theorem said, look at the rank of this matrix, and if it's not full, if it doesn't have full rank, then this collection must be dependent. But what can we say about the rank of this matrix A? What can we know about its rank? Well, if we work this down into reduced row echelon form, the rank corresponds to the number of non-zero rows in that reduced row echelon form, right? But that also means it's the number of leading ones in the reduced row echelon form. So there's a couple of different perspectives on the rank. We can think of it as the number of non-zero rows in the row reduced echelon form, but since every row that's not a zero row has to be leading with a 1. There's got to be a leading 1 there. So we can think of it as the number of leading ones in the reduced row echelon form. But there can't be more leading ones. Remember, every leading 1 sits by itself in its column, right? So that means that the number of leading ones can only be as many as there are columns for them to sit in, right? And so the number of leading ones in the row reduced echelon form of this matrix must be no more than the number of columns, right? Okay. But there are m rows, and so the rank of the matrix is less than m, which is the number of rows. And that means that the matrix A does not have full rank. By necessity, if we were to row reduce this, we would see rows of zeros sitting at the bottom, and we would come to the conclusion that this set of vectors, right, is a dependent collection, right? Those vectors must depend upon each other in some way. So that's the gist of this. It's a wonderful result, and it's resting on top of that previous theorem that said we can test independence and dependence by feeding these vectors in as rows rather than columns. So it's a beautiful result. And it tells us something that I think is quite natural, right? When you're in n-dimensional Euclidean space, by the time you've stuffed m vectors in there, right, more vectors than you can handle, you must be forcing dependency into that collection. Okay, that's what this theorem is telling us, and that's a very important result. So that brings a close to the section 2.3. I hope you've learned something. I'll see you again when we take up some applications in section 2.4. Until then, take care.